everybody. Welcome to another kind of programming tutorial. Today I'm going to talk a lot about bash scripting and, as an example, teach you how to make a ChIP pipeline out of a bash script. So I'm going to use a couple of terms. One is like shells. So shells are just an environment. An environment is where you have variables set and an interpreter. So when we talk about bash, bash is actually an interpreter, which means it reads in human language and converts it into computer language. You can have like another shell I typically use is a Python shell. So if you go in and just type Python, you now enter into a Python shell where the interpreter is Python. So if I try doing like echo dog, which would work fine in a bash shell, doesn't work because Python doesn't speak bash. So we're in a bash shell right now. Now I can say echo dog, and that works. So essentially what we're doing when we write a bash script is we're writing something that can be opened in its own shell and run independently. So since we work on the command line mostly in a bash shell, anything you type on the command line can be put into a bash script and automated. So let's get started. We'll create our program that we're going to call chipseek.sh. And I give it the .sh extension. That's technically a shell script instead of a bash shell script, but this makes it so Vim color codes everything nice and pretty for us. Okay, so typically the thing you should do when you write a script is tell the script exactly what it's going to be used to interpret it. So this is called a shebang. You can remember it's a hash and then a bang, exclamation mark, and then you give it a path to the interpreter, which is, if it's bash, will be in the root bin directory. For us, we're also going to be making this a Slurm script, so I won't go into the Slurm stuff, but we're just going to put a little thing up here that tells it that you give it up to 4 hours to run on at least a 20 core node and running on the Girth group partition. Okay, so what do we want to do? For a shell or for a chipseek pipeline, we got to do a few things. We got to align it, and we got to call peaks. So that's pretty much all there is to it. So I'm just gonna walk you through how to do that, and then we'll add an extra section called additional analysis. So anything that's got this hash, or the correct term for it is an octothorpe in front of it, bash treats that like a comment. So basically the interpreter completely ignores things like this. So that's why we can put instructions for other programs into the script with that in front of it. Or we can write notes for ourselves, or other poor schmucks who have to go through our code later. So you'll note, if you ever look at my code, you're not gonna see a whole lot of these, but that's a bad habit. It's nice to comment up your code for people who have to look at them later. So, okay, what are we gonna do here? So how are we going to align our files? So typically in our lab, we use Bowtie. So on the command line, we would just type out a whole Bowtie command. So Bowtie is the program, and we'd give it some arguments, or what you call the additional things you add, to tell it what to do. So let's see here. I'm just going to grab this, and we're going to walk through what this is doing. Okay. Okay, so here is a Bowtie command. So let me retype this out. So we'll just type echo. So echo is now going to spit this whole program out, or the whole line out, and interpret variables. So let's talk about this. Okay, so first of all, on the command line, obviously you can give it a program like Bowtie, and then Bowtie will take in arguments, and a lot of times programs like to break up those arguments with things called flags. So typically what you see with either 2 dashes for long arguments or 1 dash for short arguments, these are flags. So this is basically telling the program what inputs you're giving it. So you could make a program without flags, but this is just to make it easy so that people can optionally put in some input and not others, and also put it in any order they want, as long as they've got the right flag in front. So this argument here is just basically telling Bowtie how to split up the memory so it doesn't blow it out, or in this case it actually uses a little bit more than standard, I think. Telling it to deal with the best alignments, a few other things like that, and put out a SAM file. And kind of the more important one for us is this -P, which tells it to parallelize it, so not just try and run on one core, because on the computers we're working on, they have at least 20 cores, so we can make it go around 20 times faster. And so we give it this argument slurm CPUs on node, which I'll explain in a second, and then it wants a genome to sorry, I'm yawning. It's 3 in the morning. I'm doing this now so the kids won't be screaming in the background. Anyways, it wants a genome, so it needs to have Bowtie indexes to align it, and then I've got this control basically for further on in the program, so it knows whether this is the input or if this is experimental data for the peak collar. Okay, so let's walk kind of through this. So you'll see a lot of these $, these words with $sign in front of them. So what those are is those are just variables. So hopefully you know what a variable is from high school math. But let's say you want to have something set that you don't want to have to type out every single time. So let's see here. So let's say age. So I'm 33. So I can say set the variable age equal to 33, and then anytime I reference that, in order to call it back up, I have to do $, and then age. So now it'll say age is 30, or it'll just spit out 33. So then I can make like a short script, and I can say echo your age. Age is $age, and now it says your age is 33. So anytime you see that that $sign in a word, that's a variable that's either set by you or set by some other program. And if you ever want to see a list of all the variables, if you just hit $, and hit tab twice, those are all the variables that are set right now. So things like $home, that's like your home directory. Interesting echo $ cores. I've got this set up. That's how many cores are on this computer. So there's a lot of those different variables, but if we go back to the program, you'll see we haven't set any of these variables. And you can check if a variable is set with a quick test. You just say if double square bracket space, make sure there's a space when you do these if statements. If, and then you can put in your variable name, age, semicolon, then echo true, else echo false, don't capitalize echo, P. So this is just a simple if statement, which we'll go into in a second, that basically says if this is set to something other than nothing, then echo true, else echo false. So we said it earlier, and so we know that's true. But if we try something like, we have definitely not set that variable. It's on that list above. I'll say false. Another way to do the opposite is with the -z flag, and -z basically says if it's not set. So it's like the opposite. You could also do this. So that's saying if it's not set, then that. I think it's just easy to remember. So that's saying age is set. So if not set age, then echoes true. I don't know. This is way too confusing. So let's go back to the program. Sorry for that detour. Okay, so we've got our Bowtie command. So that's something that you've typed out. So typically you, on your command line, you would have typed out something like Bowtie chunk MBS -m1-t -best. -t, I believe, just makes it print time information out. -s -l 32-e a. So these are just quality statements. Okay, so this slurm CPUs on node, that's a variable set whenever you log into a node. So this won't be set on the head node. So here, let's look here. So if I do echo $slurm CPUs on node, we're not on a node, so that's not set. So this is a good way to check if the user is logged onto a node. So if we do slurm CPUs on node, so if we say if this variable is not set, then we can add some nasty message that says echo get your butt on a node. So echo good. And so we're not on a node, so we get our nasty message, and then you can exit the program. So okay, so that's what that's doing, and then it's just saying use every possible core that there is to do this alignment. So for us, we would have done just something like 32, because, well, 20, because that's how many we would have on one. And then the alignment genome, I've got my genomes in my home directory in the HG19 folder. So if we just look at what's in that folder, you can see I've got my HG19 Bowtie EBWT are the Bowtie indexes. So it just wants the HG19 because that's the prefix for all these, and then there's, obviously a couple different indexes. that it split it up into. Okay, so for us just spitting out the program the first time, we would have just typed, let's give it the full path here. So if you want the full path to something, you can use the real path program. So this is what's termed a relative link. So this, here. So if you type tilde, it essentially is a shortcut to your home directory, which is at that real location. And so I went the real path to the HG19 folder, which tricked you, isn't actually in my home directory. That's just a soft link to it, which is like a shortcut. So here's the real path to that folder. So then you would have typed that out, and then HG19 is the prefix, and then we would give it an output name for the for the file. Hold on a second. Okay, I was just consulting my code. So where I have a $ control here, this is actually, I've got asked for two different things. The control file and the experimental file. Control is the input. So you would have done input.fastq as your file. And this normally would print out all of the alignments to your screen, which is worthless unless you can read hundreds of thousands of lines really fast and then type them back out. So if we want to save it to a file, if it's writing out to your screen, that means it's going to a file descriptor called standard out. So standard out, it's just, if you write to standard out, it'll print out on your screen. So we don't want it to write to standard out because that's absolutely worthless. So we'll use what's called a redirect, which is this. And it points out to this, and we'll call it input.bam. So that'll spit everything into a file called input. Okay, so that's what we would have done. And then once we had that done, eventually we're going to want this sorted and in a BAM format. So, oops, we should call this input.sam. So SAM is a human readable alignment file, and that's the default output for Bowtie. So then we would have wanted to sort this, so we would have used a program called SAMTools sort. So SAMTools is a program, sort is a subprogram, and then we would give it some arguments. So this -at is like the -p flag for Bowtie. And in this case, you would have just probably typed 20-O. It's asking for the output format, which is BAM. And then -o is asking for the output file. So in this case, if you're just writing this on the command line, you would have just said something like input.bam. So this will basically take our input.sam, read it in, sort it, and print it out. So the last argument is going to be the input file. Okay, and so once this is all done, then we would have had a thing called input.bam. Maybe we'll call it sorted input. Just to let us know that it's sorted. And then we would have done this whole thing over again for our experimental one. So to save ourselves the time of typing this all out, we're just going to put in these two lines. And the only thing you would change call this experiment. Then we would have had our experiment aligned and our input aligned. And now the next thing we want to do is call our peaks. So to use max, we want to set some specific environmental variables that may not be set quite right. And the easiest way to do that is to source this python.sh file. This is from back in the day before they were using modules. And then we want to run our max program. Okay. On here. All right. Sorry about that. I lost my file that I'm looking at. Okay. So max. This is the command I use for max, and I'll walk you through this. So this is a good time to talk about paths. So paths are one of the best things about Bash, which means you don't always have to know exactly where a file is. So we talked about relative paths and full paths. So this is a full path to the max2 program. You may so here, let's just talk about paths real quick. So if you say echo $path, that'll bring up a list of locations that are separated by colons. And these are places that if you type a program name, if it's not in the directory you're in right at that moment. So right here, the only file in here is ChIP. So if I ask for a program like echo, it's not here. So echo is actually a program, and everything you type after it is an argument. So if you want to actually know where echo is, you can type which echo, and the which program will go and find it. So so echo is in /user/bin, and if we were to go through the path, you would find user.bin or user/bin in there. And so basically it says, okay, echo's not here. Is it in any of these folders? And the first one it encounters, it says, okay, we'll use this echo program. So that's why I typically create what's called a bin folder on my home directory and add that to my paths, so that when I write programs, I don't have to give it the full path to that program. Unfortunately, we can type which max to. It'll grab other ones that, depending on how your environment is set up, it may look somewhere else for it. So for consistency, I have been I've been giving it the full path to this max2 version here. So that's why I have that all typed out there, because that basically ensures that the environment that I set up with this source script just basically means execute it and export all the variables into the shell. So that just makes sure that this aligns perfectly. Okay, so again, we'll make this an echo. So let's do that same thing here. We'll just copy this thing and make sure it's oh, why'd you do that? Okay. Make sure that it's echoing this so that the user, when they're running the program, if they're running it interactively, they can see what step it's at and what it's actually calling. Okay. So here we are. Let's step through this command here. Really? Okay, so we've got the max program here at the start, and then we're calling the subprogram call peak. And basically the only argument that we're really giving it right here is the p-value. So normally it uses your standard 0.05 for a false discovery rate. But here we're running a little more stringently, asking it to give us peaks that it's very confident in. That's just something we kind of do in this lab. We also typically run it with just a standard p-value as well to try and, some things don't call as well based on how your sequencing went or what the ChIP profile of the actual calls looks like. So we do it both ways just in case. Let's see here. I'm just trying to remember what treatment does here. Okay, so I have this kind of split up weird in the script that I'm pulling this from, so I have to go back and remind myself how I have this set up. So -T treatment is your experimental input. So that's where we're going to grab this sorted experiment.bam. -C control is going to be your input. So that's where we're going to grab our sorted input.bam. And we're telling it the format of the inputs is the is a BAM file, and -N is the output file. So then we're going to call it peaks. Call this peaks. And it's actually going to put out a few files, so it just uses peaks as the prefix for all these files. So we'll give it a better name, like max2. Still not very informative. And then it's also going to spit out a bunch of stuff to the standard out. It's not going to be putting the output to the standard out. Thank God they put a little thought into this, but it will put out messages. So if you're running this automated, it'd be good to catch those messages so that you can look back and feel confident that you got everything. So that's where we're using these redirects, and so we use one that will say max to output here, and then there's actually two things that'll print out to your screen. There's what's called standard out and standard error. Most of the time you want the useful output for a program to go to standard out, and then you want any like messages that the program is giving just to the user, or warnings or errors to go out to a file descriptor called standard error. And both of these will print to the screen, but it's a way to separate out error messages from program output. And max has both, so we can do max to error.out. We'll call it standard error. So we'll grab both of those. Okay, so hypothetically, now that thing will run, and then once it's done, we're gonna want to do a few other things with it. Okay, so one of the things that we typically do is we like to grab motifs that are enriched in the peaks that are called by max, and part of this is just kind of self-checking to make sure that we actually are chipping for the motif we have. So if you know what it is, like CTCF or something like that, or ER, you can look for those motifs and confirm that you found what you thought you found. Otherwise, you may be looking for something like trying to figure out what motif it actually binds to. This is also useful for that. So, why are you not copying? Let's see here. This thing's being kind of ornery. This is kind of strange. I may have to type this whole thing out. Okay, here we go. So, Max puts out a lot of things, including summits file. So, it's got the prefix that we saw up here that we gave it, and it'll say Max. Let's see here. Let's make sure. Max2_summits.bed. So basically what we're doing is we're using the sort command to sort it numerically reversed, so highest number first, based on column 5 of this, and column 5 is just the p-value. So we're looking for the peaks that it was most confident in calling, and the summit is just where the Max thinks the very center of the peak is. And so I guess this is a good time to talk about a pipe. So we could write this out to a file and then run head on it. But pipes basically allow you to skip an intermediate file step. So rather than writing it out to a file and then running head on that file and then saving that as something else, we're just run max. We run the sort command, and then when it finishes running, it then spits its output to the head program, which grabs the first 500 lines. We're just looking at the top 500 peaks. We're going to spit that out to a file called toppeaks.tab. All right. And then once we've got that toppeaks.tab, we're going to grab the, so essentially this is just going to give us a genomic location with chromosome start and stop, and that start and stop is going to be a 1 base chunk. So what we want to do is we want to go then into the genome and pull this out. And I've got an older version. I got a newer version of this program that I'd like to use, but we're just going through this real quick. So basically, we're going and we're looking at, I've got these FASTA2 files, which are essentially just the whole genome with all the new lines removed. So the genome is in, each chromosome is in one line. And we just go through and use this little script I wrote called motifextractor.awk to grab all the positions from our top peak file, and then just grab those sequences out. Let's see here, what was it doing with these variable names? So basically this grabs the anyway, so this just the way I wrote this is it's looking for our top peak file. So here we'll just do top peak.tab, top peaks, make sure you call it the right thing. And then what it's doing is it's just, there's one of these FASTA2 files for every single chromosome. So it's going through and it's looking for every single one of these. So here, just to give you an example, of what this is doing. So we say 4x in this. So if I run this here, oops, gosh, that makes done. Alright. It essentially is creating a list of every single one of these files. And then once it's created that list, it's going to run that command on every single member of that list. So essentially it's going to grab all 23 and me chromosomes and run this command on each one. And then this program is going to spit it out to a file that has this Sorry, I have to review these programs. I wrote these things like 4 years ago, so remembering what they all do is a little tricky. So essentially, it's going to write this out to a folder that I should give it as a name here. So we'll come back to this. But essentially, we're going to get a program or a file called peekseek.fa, so a FASTA file. So it's just all it is a name and then some sequence. And then let's see here. I've just got this thing on the side of the screen that's covering that up, so I need to see what's going on here. Anyways, so I'm going to teach you a little trick here. So when you're running things on bash, it will run the command you have and it'll stop you from typing any input until that command is done. But in reality, computers run a lot faster than humans, so it can do multiple jobs at a time, and bash can farm jobs out to multiple cores. So when you're using the command line, you're typically only using one core at a time, and we've got at least 20 cores, and we've got 22 chromosomes. So rather than having to go through each chromosome one at a time, we can add a little ampersand at the end. And this basically says, okay, when you start the job, send it to the background. And if I can keep working, and just have that run in the background. So what we're doing is essentially saying, okay, take all of these 23 or 24, I guess, if you have the Y chromosome in there, all these jobs and run them all at once in the background, spreading them out among the cores. And then if we add this little wait command, that means it'll wait until all of those background jobs have finished so that we can continue on. So that speeds things up. It's essentially like using the -p command up here to speed things up. We're multi-threading technically. Okay, so now that's done. We've got our FASTA file. Now we got to run our wonderful program called meme on it. And meme is just a program that calls, goes through and looks for enriched motifs. And so, meme, this is the command I've got for it. So there's a few tricky things going on here, which is why I put these into programs. So we have to use this MPI execute Hydra thing to make this meme run multi-threaded. So that goes out in front. And then we give it the full path to meme. And we give it our file that's coming in, which will be, what did I say that name was? Let's see here. The name of it was our peekseek.fa. Let's just put a little comment here. This is writing to track of things. And then meme takes this -p to tell it to parallelize, but again, you need that MPI execute.hydra thing in front. I don't know why. It's just some weird part of our what's it called? How the compute cores are set up. And then we basically give it our arguments here, and then we say output folder. We'll just call it meme. And so that'll make a folder called meme with all the little files that meme outputs into it. Okay. Let's do one more thing here, and that is runs. We'll just call this good actually. My pipeline runs CISH, but that's a little convoluted in how we do that. Okay, so this has probably been extremely confusing, and if we do this, we're going to have a whole bunch of files all in one spot. So I'm going to take all these command line arguments and kind of string them together into an actual program now. Okay, so the first thing we want to do is it's just kind of a good idea to put everything in one spot. So what we can do is the first command, we can take arguments in our program. So again, arguments are the things that are written after the command name. So for this, we'd say something like name. So we can say name equals, so we're setting a variable called name. We can just say, give me argument number 1. So when you run a bash script, it's going to take all the things following the script name and assign them to these variables. So $1 means the first argument after the script name. So we'll just do that. So we can give everything a common name. And our first step we'll do is make directory $1. And then we can say experiment equals $2. So that's going to be your experimental VASQ. Let's call it VASQ equals $2 and experimental or input VASQ equals $3. So what we're going to do is just to keep everything in one spot, we'll link $2 into $1, link $3 into $1. So essentially, let's just do this $name, link $experimental VASQ into our folder, which will have our experiment name, and then we'll link input So now we've got our FASTQ files in there. Linking just is like making a shortcut. So we're just moving them there, but we're not copying anything. We're just putting them in there without moving the original file. So we've got we've basically got copies in both for space, both spots, but they only take up the space of one file. It's magic. Ask me about it if you want me to explain it further. Okay, so now we've got our FASTQs in that spot, and now we can just cd into that folder. So cd into name, $name. Let's just do this for consistency's sake. And we'll put a comment here, and we'll say make directory and move FASTQs there. not move, link. All right, so now we're enter 3. So if you gave them the full path to say these FASTQ files weren't in the folder that you're running this program in, and you're like giving it full paths to ones that are different locations, you can, now that we've got them in there, we don't want the full path when we're calling them. So we are going to do this. I'll show you. We're going to use what's called base name. So what this does is if you have like a location file.txt. So say you've got a full path to a file. What base name basically does is just strips everything off except for the file's name. And you're probably asking, okay, what's this parentheses thing with the $sign in front of it? If you do $sign parentheses, anything that's inside that parentheses is going to be, the program's going to run, and the output, it will just fill in that output. So essentially it's just going to get the base name of this FASTQ file and assign it. So we're reassigning the variable. And, okay, so now we've got those FASTQs there. Okay, so now what we can do, the last thing we should grab is the genome that we want to use. And it goes $4, so they can put in something like HG19 there. Okay, so if we go down here, now we can say, okay, here's our input.fastq. So we're going to change this to the variable name, $, input fastq out. And we're going to use that $name dependably here so that everything we have has that suffix on it. This is a nice way of just saying keep the variable separate from other things. I'll show you here in a second. So basically we're taking our input FASTQ, we're writing it out to our .sam. So I've actually got several different genomes in this location. So I've got HG38 in a similar setup where it's the indexes are named inside of a folder with the same name. So we can just do $genome, then $genome. So now it's not hard set what genome they're writing to. And I told you that we can use pipes to avoid having intermediate files. So we're actually going to do that right here. We're going to bring up the next line, and we're just going to pipe the standard out into the samtools file, and it'll actually sense when we do that, so we don't need that input.sam. And so then we can change this name of this thing to sorted underscore $name.bam. Okay, and so that will allow us to, it'll just name it correctly inside that folder. So it'll be, the folder will have the name, and then everything inside of it will have, let's put the name first. $name underscore sorted dot bam. So it'll spit out a, we also need to tell it that this is input. Input underscore sorted dot bam. Okay, and we're going to do the same thing here. So we're going to change our folders to $genome. $genome. And then $experiment FASTQ. And then we're going to pipe it into SAMtools. And then we're going to do $name underscore input. No, this is experiment sorted dot bam. Okay, so the reason I'm putting those brackets around that is if I try doing $name underscore experiment sorted dot bam, it's going to look for this entire thing as a variable, and obviously we don't have that, so the curly braces just help it know where the variable name ends. Okay, so now we've got that. Now we can go down and kind of do the same thing for our max2 call. So we can say $name underscore experiment sorted dot bam. And for control, we do $name underscore input sorted dot bam. And since these are in the folder, we're not going to give them the prefix. I'm not going to worry about that. And then we go down here. Good. What we can do here, again, in this folder, we're not going to use this top peaks file out anywhere else, so we'll leave the naming the same. But we do sorry, I forgot about this. So we do want to add one thing here. We'll add the name here, $name underscore. Instead of max2, we'll just do $name underscore. And so that'll just append this $name underscore to the front of all these names. And so now, instead of max2 summit, it'll be $name underscore summits. And then going through this, this program actually wants a slightly different thing. So it'll want the $name variable here. So it's actually just asking the path to this file. I'm sorry, this program, I wrote it a while ago and it's kind of goofy, which is why I'm a little confused about how it behaves. Okay, so it's actually looking for the folder that it needs to write stuff to, and we're just going to say write it to this folder. That's what the period means. It's just the folder we're working in at this moment. So yeah, we're just going to put that in there. And then as we keep going, so now we should have our output. And then the last thing we need to do so it'll create that peek-seek file once it's done. And then I think we're okay just writing this out to a folder called meme. So once this is all done, you'll have some sorted BAMs. You're going to have all the outputs for Max, and then you're going to have the output for meme in the folder. One last thing that we might do is I think it's a good idea to have all the commands that you're actually running printed out to a file. So most of the time you're not going to run this thing interactively. You might, and it's good to know what's going on. So, but for the most part, you're going to want documentation of what the heck happened, and if anything went wrong, you can go back and look at it. So what we can do is we can have the best of both worlds using a program called T. So we can say echo that command. We pipe it to a program called T, and what T does is it allows you to write something to a file. So we're going to create a file called $. Let's call it $name underscore commands. What we're going to do is we need to give it the -a so it appends to this file. And that'll let us know what commands we wrote. And it'll also print them out to the screen, so it's like doubly beneficial, so you can see it currently and also see what you ran in the past. Sorry about that. There is a stupid button that I'm not sure how to move for this recording software. It's sitting right over where I need to write. Echo that line, type T out to, -append, $name, and some text. Yeah, so you get the idea. I'm basically just running this whole thing over and over again. Stupid thing, copy and paste. Lordy, I don't understand what's going on with my copy and paste here. Alright, there we go. And this should be the last one. We're just going to pop this guy in here. Blip, blip, blip. So essentially what that's going to do is that's going to write out all the commands, and then we can add our own stuff if we wanted to here to tell us what was going on, but I don't think we really need that. The last thing that would be good is to grab the variables and put them out into that thing. So echo name equals $name. So this commands, so if we're not using T, then we need to use a redirect to write out using the echo command. And if you were to, let's see here, so if I were to just do this, what would happen is it would overwrite this file, and so that would be the only line in this file and overwrite this original one. So if you want to append to a file, use 2 carets here. Just a fun fact. Why are you? My mouse buttons are giving up on life. Almost there. IPGM equals $sign genome out to that thing. Okay, so that should tell us pretty much everything that happened. I'm not going to run this now. You can go ahead and try and run it yourself if you wanted to. The path to it is here. You can try and run it and see if it runs as expected. And if you have any questions about any of the things I went over, I know it's pretty brief, let me know and I will try and address those. Other than that, have a good morning.